crowds here. How's your cruise going so far? Hopefully you've been enjoying all our guest speakers. I asked that earlier, and this gentleman is really one of my favorites in the fleet. Every time I get a chance to work with him, I know it's a home run for you, the guests, to learn everything about what's up there. So ladies and gentlemen, please welcome Dr. David Hughes.
Well, thank you very much, everybody. You can all hear me. Today, I am talking about the sun. And of course, the sun is our star. And of course, it's the object which makes you all astronomers. Because let's face it, you can all recognize the sun in the sky and the moon. Those are the two, to me, most important objects up there. And then, of course, you can move on and look at other things, and it's a great introduction. But the sun is more than that, because the sun is our star, and it is seriously important. It is the object that keeps us warm, and keeps us alive, and provides our food and our fuel. So, when I spoke the last time and said it doesn't affect the price of fish, I was lying a bit, because the sun does. If the sun went out 8 minutes, 19 seconds later, we would seriously know about it. And the sun also has a very special place in my heart, because when I finished my physics degree and then went to Oxford to do astrophysics, I studied the sun. In fact, I wrote a thesis on the polarization of the visual radiation from the solar continuum. And this entailed me building a telescope, getting the data, and then analysing the data in great detail, and of course, ending up with a doctorate. So the sun, to me, is very important. And interestingly, when I finished my degree, as an astronomer, I only knew where one astronomical object was in the sky. And you do as well, because you can go outside and you can see the sun and you've got it. The snag with the sun, though, is that for cruise talkers, it's a bit of an enemy. And that's why I'm so pleased to see you all here, because usually, when the sun is shining, you're upstairs sunbathing and not sitting downstairs listening to old blokes like me. So, let me introduce you to my old Obbo. And when I was at Oxford, the alarm clock was always set for half an hour before dawn. I used to get up, open the curtains, look out. If it was clear, I had to get on my bike and cycle to the observatory. And of course, if it wasn't clear, if it was cloudy, I went straight back to bed again. And that was rather nice. And this is the observatory of the University of Oxford. And of course, it's exactly where an observatory for the sun should be. Oxford, a wet city in England, and nobody, and I mean this now, nobody observes the sun from England anymore. I used this telescope here and had many happy hours up there measuring solar polarization. So, as I say, the sun is important to us, and I have a talk which I give on lots of ships about how the sun moves across the sky and how the ancients observed this movement and worked out what time of the year it was and so on. So here we are for a typical Northern Hemisphere observer. I apologise to my Australian friends. I should have to put the picture in backwards for you. But anyway, for a Northern Hemisphere observer, what happens is the sun rises in the east, well it does in the Southern Hemisphere too. It transits across the sky in a great loop. And of course, in the summer, it stays in the sky for much longer than it does in the winter. And also you will notice that as the seasons change, the rising and the setting position of the sun varies. And this is important, always important to ancient people. And in England we built Stonehenge to take this sort of situation into account. This business of the sun in the sky always fascinates me. Astronomers love looking at the sun up there and working out what's going on. And last year in March, I was on a cruise going up to the top of Norway to look for the aurora borealis. Here we have a picture taken in Norway, not in March, but in June. And there, of course, the sun never sets. Somebody has taken a lovely picture every 2 hours throughout the 24 hours of the day, and you can see the sun here at its maximum altitude, and here at its minimum altitude. And here, of course, we have noon. Here we have midnight. And for the astronomers in the audience, the difference between these two altitudes is 180 degrees minus twice the latitude of the observer. For the rest of us, we can ignore that together. But you can see how the atmosphere is affecting things. Here, the sun is very low in the sky, coming through lots of atmosphere, and here the sun is very high in the sky, and the light from that sun is less absorbed. So, just let me stress this. The sun is important to us, to all of us. When the sun's there, what do? You take your clothes off, and you lie in it, you read a book, you enjoy yourself. And this doesn't just happen to humans, it happens to animals as well. They like the sun, it warms them. And I don't know what your cat does, but this is exactly what my cat does. So here we have this wonderful object, our star, and I'm just going to spend 40 minutes or so trying to explain why it is so important. Firstly, I've drawn a completely out of scale picture here, which is really an advert for another talk I'm giving on this ship, which is about our planets and planets around other stars. But you can see the sun here at the center of our solar system, and it's been hugely exaggerated in size because, in essence, the sun is only 109 times bigger than planet Earth. And what we have, of course, is Mercury, Venus, Earth, Mars orbiting the sun, as is Jupiter, Saturn, Uranus, and Neptune, and we have these comets coming along and asteroids. The important message, though, from this picture is that when it comes to the mass of the solar system, the sun accounts for 99.85% of that mass. So in essence, when it comes to the solar system, the sun completely dominates, and these little things are much less than the sort of tip that an average American would give in a restaurant. And this business of having the sun in the center of the solar system was all down to this dear old chap. And here we can see Nicholas Copernicus. These are the dates, his birth date and his death date. And as he was dying, he actually published his major book, which revolutionized science. And I'm not going to read this out because my Latin is appalling. In schools in England, if you wanted to be a scientist, you weren't allowed to study Latin. You had to spend all your time studying science. So I don't know how to say this properly. But the important thing is that Copernicus drew this diagram, and here at the center we have the sun and we have the planets going around it. Whereas before Copernicus, people had the Earth at the center of the astronomical cosmos. A stationary Earth with everything moving around the Earth. Copernicus fixed that, changed that into this true picture, and then after him, everything slotted into place. We started to work out what the orbits of the planets were. We started to work out why they had those orbits. Isaac Newton came along and did that for us. And in fact, Copernicus started modern science. So, this is what I'm talking about. And let me stress first of all that the sun in the sky isn't very big. You walk around with measuring instruments always with you. And astronomically, we measure angles in degrees, and when it comes to the sun, it subtends half a degree at the eye. Now, there are 90 degrees in a right angle, and the sun subtends half a degree. If you extend your finger at arm's length, this finger covers 1.5 degrees of the sky. So try it when you go sunbathing this afternoon. You can cover the sun up, it only subtends half a degree in the sky. And of course the moon does the same. In fact, luckily, in a week's time, the moon extends slightly more than half a degree, and therefore will be covering the sun up. But I just love the sun. Being scientists for a minute, you will notice some data facts about the sun. It is spherical. It is yellow. Using those two facts, we know A, it can't be spinning very quickly. If it was spinning quickly, it would be an oblate spheroid. And B, because it's yellow, we can use the physics of radiation to tell us what the surface temperature is. And so, let me just bore you briefly with some solar data. And this we will go through fairly quickly, but we'll just give you a hint as to what the sun has got. I've already mentioned the fact that it contains 99.86% of the mass of the solar system. And this makes the sun a proper star. And something like Jupiter, which is a decent-sized planet, well, the sun is 1,048 times more massive than Jupiter. And so in astronomy, there's a great division between stars and planets. They are nowhere near the same objects. When it comes to our planet, Earth, well, the sun is 330,000 times more massive than planet Earth. It's 109 times bigger. And of course, distance. The sun is a long way away. It's in fact, you can see it here, 1,496,000,000 kilometers. It takes light 8.3 minutes to get from the sun to planet Earth. And here we are at 1,500 million kilometers away. It's a decent distance from us, but it is ridiculously much closer than the next star. The next nearest star is 200,000 times further away than the sun is. So I've mentioned the angular size. 2 days ago I mentioned the surface temperature. Here we can see the luminosity. This is the energy it gives out. This is the metallicity. This is how much of stuff it's got there which isn't hydrogen and helium. And it's this metallicity which is vitally important. Because the sun has such a large metallicity, there are lots of metals around to make things like you, ships like this, and planets like Earth. Spin period. The sun goes around about, well, just a bit less than every month. And here we have its age. Here we have an important number here. The sun is about 4,570 million years old. And this number is extremely similar to the age of the Earth. In fact, most astronomers nowadays think that the sun and the Earth were produced in exactly the same process. But unfortunately, that's a 12-lecture course at the University of Sheffield, and I'm not going to go into the gory details. So, when it comes to the sun, how does it compare with other stars out there? Now, this is a bit of a funny diagram, but for every massive star, you get loads and loads of less massive stars. And the sun, in essence, is just in the top 5%. 95% of the stars in the sky are less massive than the sun. And interestingly, in 1926, a very famous English astrophysicist at Cambridge discovered this graph. And I'm not going to use many graphs, but astronomers do love them. On this graph, we have the mass of a star on this axis as a function of the luminosity, the energy output of a star on this axis. And you will notice straight away that the more massive a star is, the more luminous it is. In fact, it's a lovely relationship. There's a beautiful line going through this. The relationship has a power of about 4 in it. Eddington discovered this and then spent a good few years trying to suss out why it was happening. So if I say that the sun is in the most massive 5% of all the stars in the universe, this diagram indicates that it is also in the most luminous 5% of all the stars in the universe. We mentioned briefly in the last lecture where the sun comes from and where it's going. And this is important because the stability of the sun is important when it comes to life on Earth. And what happens is the sun started off in a cloud of gas and dust, which was given a bit of a bump, probably by a supernova explosion that occurred nearby, and then started to condense. And this cloud of gas and dust would have then condensed into a family, an open cluster of stars. We then ignore the sun's brothers and sisters and just consider it, and the star would become hotter and then spend many, many years as a yellow dwarf star. It would then blow up, eat up the orbits of Mercury and Venus and those two planets, completely evaporate the atmosphere of Earth, and then it would die and become a white dwarf. So what we're saying here is the sun was born in a cloud of dust. In its death throes, it would completely ruin all these interior planets. And of course, this is the sort of group it was born in. And here we can see a lovely example of an open cluster. This is in fact on Cygnus, Messier 39. I've written here how far away it is, 800 light years. This is the funny thing in astronomy, of course. You're not here taking a picture of an open cluster as it is now. You're taking a picture of an open cluster as it was 800 years ago. But this open cluster will last in space for about 500 to 1,000, 500 million to 1,000 million years. And then the stars in it the stars will just disperse and scatter themselves in the galaxy. And so the sun would have started off here with lots of brothers and sisters, but of course is now just by itself and is about 4 light years away from its nearest star. This is a possible source of the sun. Here we can see the Eagle Nebula. It's this sort of thing that would condense to form the sun. And of course in my last talk I showed you a close-up of this region here. But what you're seeing here is lots and lots of gas and dust in the Milky Way which can condense to form stars. And when the sun goes from its stable state to its white dwarf state, it blows up and actually ejects its outer atmosphere. And here we can see a sort of planetary nebula. This is rather odd. This is one of the big problems that you get in astronomy. You're looking at a picture here, which is just two-dimensional and flat, but it's not really. You're actually looking at something which is a three-dimensional object, but the photograph has just flattened it against the sky. But you have this lovely situation where, when the sun becomes a white dwarf, it blows its outer atmosphere off into space, and that material that's blown off can be then used to form other stars. So the sun, with its metallicity, is known as a second-generation star because it's formed out of stuff that used to be in previous stars and previous supernovae. Well, I'm just going to hit you with one other rather awkward graph, and that's this one. This is the most famous diagram in astronomy. And one of the snags of being an astronomer is that if you really want to know where stars come from and how they evolve, you have to get yourself used to using this diagram. And this was first produced in 1910 by a Danish chap called Hertzsprung, and it was then produced in 1913 by an American chap called Russell. And all they did was get out a piece of graph paper, and on this axis they plotted the surface temperature of the stars that they could measure, and on this axis they plotted the luminosity. And instead of the stars being scattered all over this diagram, they found that most of the stars, in fact about 98% of all the stars in the universe, occupied this line here across it, which is known as the main sequence. The sun is here. So For all these main sequence stars, there are a few white dwarfs which had died, and a few giants and supergiants which had come off the main sequence later on. And the importance of the main sequence is that's where a star is when it's simply converting hydrogen into helium. When it comes to the sun, if we plot on this axis the surface temperature and on this axis the luminosity, the sun would have started off here in a cloud. It would then have moved on to the main sequence and actually produced our planets in this position. It would then spend 98% of its life on the main sequence, move off to become a red giant, and then die. And so by studying the Hertzsprung-Russell diagram, you can get a feeling for stellar evolution, and many scientists do little else but study the Hertzsprung-Russell diagram all their life and plot it for all sorts of different groups of stars. So, just to recount again, we have the birth, the production of planets, a huge amount of life as a main sequence star, and then the sun blows up, becomes a white dwarf, and dies. And luckily, you will see here age, and you will notice that this region here lasts literally about 10 billion years. So there's plenty of time for life to evolve and for us to progress and for civilization to break out. What is happening when it comes to stellar evolution is that we're here now, and as time progresses, you can see here we have luminosity, radius, and temperature. The temperature of the sun won't change much, but it will get slightly bigger and it will get slightly more luminous. And this, of course, will heat up planet Earth as time progresses. Now, I'm not discussing global warming in this chat, but you've had it. Because if you know about stellar evolution, the globe, planet Earth, will warm up as time progresses. And so we, as the civilization on Earth, will have to do something about it. Personally, living in Sheffield, in the middle of England, the fact that it's getting warmer and warmer is lovely. So, the sun has neighbours, and here you can see a little plot of where our neighbours are. And here we have a position which is 3 light years away from the sun, 6 light years away, and 10 light years away. And this is a bit awkward, because if we are a space person and want to go from the sun here to this star and then come back again, even if we can get the spacecraft going at the velocity of light, it's going to take us 10 years to get there and 10 years to get back. And so travel between one star and another is, at the moment, unthinkable about. That's not to say that in 1,000 years we won't have brightened up a bit and be able to do it, but at the moment, we've had it. We are stuck in our own solar system. So let's just think a bit about these characteristics of stars that we see around us. If I take a sphere here, which is 22 light years across, this sphere will contain, this is a spherical object, will contain 100 stellar systems. 69% are single stars, like the sun, 22 are binary stars, where you have 2 stars together, 7% are triplets, and so on. The average distance between these systems in this volume is 8 light years. And astronomically, we can see absolutely no reason why the volume around the sun isn't fairly typical of everything else in the disk of the Milky Way. So on average, stars are 8 light years apart. And interestingly, I always used to ask my students, is the sun a typical star? Well, in some ways it is, and in some ways it isn't. But one fascinating way it is non-typical is that when you look at the stars in the sky, about 4% have planets. That's if you believe the research paper written by David Hughes. 4%. Well, 4% is plenty, isn't it? I mean, you don't want planets all over the place. 4% is enough. I'm convinced that E.T.'s out there somewhere, even though he's been a bit naughty and not got in touch with us. So what I'm saying is that the sun is in the Milky Way galaxy. Here you can see the position of the sun in the Milky Way galaxy. It's about 26,000 light years away from the centre. It's going around the Milky Way every 250 million years. And crudely, the sun, here we look at the galaxy edge on, is in a typical position, an average position. I always like this idea. I think we live on an average wet planet, around a fairly average sort of star. There's nothing really special where we are, and therefore there's no reason why our cruise should be any different from any other. So here we have the numbers associated with the galaxy, but I'll move on. When it comes to composition, the composition of the sun is fascinating. It is 74% hydrogen, 25% helium, and 1% of the rest of the stuff. And this was discovered by a very interesting lady. And I would blame this lady, actually, for making me an astronomer. In fact, I'm extremely thankful. This is one of the brightest female astronomers that ever existed, Cecilia Payne-Gaposchkin. She was Cecilia Payne, a student at Newnham College, Cambridge, and then she wanted to get on and did the sensible thing that lots of astronomers do in England, and that's catch a ship to America. And she went to Radcliffe, which in those days was part of Harvard, and then she moved into the observatory at Harvard and ended up running it. And it was this lady that wrote what is renowned to be the best PhD thesis ever written in astrophysics. And when she started, people were convinced that the sun had the same composition as the Earth, and she said, rubbish. You're all wrong, I'm right. The sun is 74% hydrogen and 27% helium and so on. And needless to say, everybody turned around and said, now come on, you're wrong. But she turned out to be absolutely spot on. A wonderful example to astronomy. When it comes to the sun, what we've got physically is something which is rather simple. It is just a ball of gas. And so it's gas at the edge, gas halfway down, and it's gas in the middle. Once you've got that idea in your mind, you then only need 4 decent physics equations to tell you exactly what's going on. And crudely what happens is the sun divides up into 3 regions. It has a core, where the energy is generated. It then has a zone here, where the energy is radiated from one region to another, taking each photon of energy about 1 million to 10 million years to get from here to there. And then at this position, you're about 25% from the surface, it starts boiling, and you get these convective cells and this turnover. So the sun is basically simple. Core, radiative zone, convective zone. You have a photosphere that you can see from Earth. That is the surface region that you can look into. You have a chromosphere that we're going to be able to see in a week's time, when the eclipse takes place, and this wonderful corona that we're going to be able to see in a week's time when the eclipse takes place. And in my next talk, which isn't tomorrow but the day after, I shall be talking about these regions, so I won't talk about them again. The sun, of course, produces energy, and this energy is extremely useful. When it comes to planet Earth, we absorb 1 part in 2 billion of the energy the sun produces. So when people say, oh, we're running out of energy, we're not. We're using 1 part in 2 billionth of the energy of the sun. And then, of course, the Earth reflects back into space 34% of the energy that hits it. And then we use the rest to warm the land and the water, to make the water go round and the atmosphere to go round, to produce winds and oceans, and also here, a very small percentage for photosynthesis. And it's this photosynthesis that ends up, in essence, producing the fuel. And so we've only got to be a bit more effective, and we can easily use the sun to produce enough energy for everybody on Earth forever without any problems at all. Now, of course, I briefly mentioned where the sun got the energy from, so I shall rush through this. This all happened in 1905. Prior to that, being simplistic, we had the foggiest idea where the sun got energy from. We knew how old it was, we knew how hot it was, and we hadn't the foggiest idea where this heat came from. Then along came this lovely German bloke, Albert Einstein, and he sorted out the whole problem. All he said was, well, not all, but the nub, was that E, energy, is equal to mass multiplied by the velocity of light twice. So energy is equal to mass times the velocity of light times the velocity of light. And it took a bit of time for people to work out what this mass was that was being destroyed and being converted into energy, but people like Eddington in Cambridge quickly realised that it was the protons of hydrogen nuclei, which were being converted into helium. If you look at this process, there is a mass difference. And so I've got a few little equations here, and I'll go through these fairly quickly because they're a bit boring. But putting it crudely, what happens in the core of the sun is that typically 1,000 grams of hydrogen are being converted into 993 grams of helium. And you can see straight away, by subtracting that number from that, you've got 7 grams that you can stick into E equals mc squared. Now what's exciting is that if we, humans, today on Earth, could do this, instead of relying on it happening in the centre of the sun, if we could convert 1,000 grams of hydrogen into 993 grams of helium, we would produce $1,800,000 worth of energy. US energy. Now the snag is at the moment that we can't do it. We're trying. We've been trying in the UK ever since the Second World War. You've been trying in the US, we haven't got there yet. But we'll get there, and then energy will become ridiculously cheap, and there'll be no problems at all, I hope. So what the sun is doing is using up its hydrogen and converting it into helium, and I'm going to do this very quickly. In essence, the sun is burning up 600 million tons of hydrogen every second. Now you might say, oh, that sounds a lot, but it's not. Since the sun has been stable on the main sequence, this burning of hydrogen into helium has only used up 0.031% of the sun's mass, the equivalent of 8,000 lunar masses. The sun is gradually getting less massive as it ages. This means its gravitational field is decreasing, and we on planet Earth are moving away from the sun. In fact, since the sun started doing this, we've moved away 50,000 kilometers, which again is not very much. This process, though, of course, is changing the composition of the sun. So when the sun first was produced and put onto the main sequence, it had these percentiles for hydrogen, helium, and these things, and it's now got those. So things are changing, and it's this change which is going to make the sun blow up eventually. Luckily, though, this process, this E equals mc squared, is appallingly inefficient. And this inefficiency means that the sun can happily exist burning this hydrogen fuel for this number of years. That's 100,000 million years. And that has been long enough for us to evolve, for plants to evolve, for us to become intelligent, to us to make motorbikes and motor cars and so on. And it's this slowness of the evolution process that has helped hugely. So, let's think about how we know about the sun. Here we've got a picture with a sun in it. And what we do from planet Earth is that we take images of the sun and that we analyse sunlight. We can split sunlight up using a spectrum, using a prism, and of course raindrops do it as well. So you can see the way the light splits up into different colours by looking at a rainbow, and we have these lovely colours in the rainbow: red, orange, yellow, green, blue, indigo, violet. And where I come from, Yorkshire in England, we always say to our children and students, Richard of York gained battles in vain, which tells you what the colours are. I'm sure in America and in Australia you say something else, and I look forward to you telling me about that. But of course, when it comes to sunlight, Because the surface of the sun is about at a temperature of 5,500 Celsius, what you get is quite a lot of the energy, about 44% of the energy the sun emits in the visual, a bit here in the ultraviolet, which gets absorbed mainly by our atmosphere, and then a lot here in the infrared, which also gets absorbed by things like water and carbon dioxide. It's these water and carbon dioxides that produce the greenhouse effect that increases the surface temperature of planet Earth by on average 35 degrees Celsius and keeps us all cozy and warm. So if we look at sunlight and split it up into its different colours, we can see in that sunlight these black lines. These were first seen by Woolston in England, but he didn't do much about them. And then they were re-seen by Fraunhofer in Germany, and so we now name them after Fraunhofer. They're Fraunhofer lines. And of course that's a fairly crude picture. This picture shows the total solar spectrum. I've had friends who've spent nothing but their whole life analysing this. And it goes from violet and indigo and blue to green to yellow and red. And you see these lines all over the place. And these are produced by cold gases absorbing the radiation from a hot source, as I mentioned in my previous chat. And so, of course, these enable you to work out the temperature and the composition of solar regions. So, people on the surface of Earth use telescopes to observe the sun. And I'm just going to show you three. This is the McMath Pierce Solar Telescope in Arizona. Beautiful, beautiful instrument. And in my old picture, what you could see, and you can't see very well here, is a truck in this garage. So this is a huge instrument. All paid for by the Americans, thank you very much. And all you do is take sunlight, reflect it down this tube into a big spectrometer that is buried underground, constant temperature, low vacuum and so on. Here's another solar telescope. This is another beauty. This is the Big Bear Solar Observatory. This is 70 miles east of Los Angeles, 2 kilometers up, and the is built in a lake. What you have in astronomy is this problem with the atmosphere wobbling, and this produces seeing problems. And by having lovely, cold, flat water around the telescope, you can actually reduce that problem. I better show you now. We do this in Europe as well. This is our solar telescope. This is the Swedish 1 meter solar telescope. And again, you have a heliostat reflecting light down here into a spectrum chamber. And this is on La Palma in Spain at the Roque de los Muchachos Observatory. This heliostat that you find up here is a lovely astronomical device which just contains 2 flat mirrors. And so what you have is the sun hitting this mirror, the light being reflected in that mirror. And then, if you twiddle around with this mirror, you can always make this second mirror reflect the sunlight down into your laboratory and do your hard work when you get there. So you can take your solar spectrum and you can work out the composition of the sun. I've already mentioned that you've got your hydrogen and your helium. For us, we breathe oxygen, that is important. The sun contains 0.77% by mass of oxygen. Our trees are made of carbon, the sun contains 0.29% of carbon. Iron is important, rocks are made of silicon and oxygen. You can see the rocky components here, and you can see how much metallicity there is. So if you add these two numbers up and subtract from 100, you can see that about-ish 1% of the sun is made of metals. This means that if I got to the sun and blew away all the hydrogen and all the helium, I could be left with a planet with a mass which is typically 3,000 times the mass of the Earth. Which would be interesting. Anyway, we can use the spectrum to look at velocities. So when I tell you that certain bits of the sun are moving at certain speeds, this is because we see the way the spectral lines shift because of the Doppler shift movement. We can use the spectral lines to measure magnetic fields. Now this is a bit of a complicated quantum mechanics business, but if you have a transition in a zinc atom which will produce, where there is no magnetic field, a line of wavelength 4680 angstroms. If you apply a magnetic field, this line splits into 3, and the splitting is directly proportional to the strength of the magnetic field. So this helps hugely. You can use the way in which the energy varies as a function of wavelength to measure temperature. So this enables us to measure temperatures of different regions on the sun. So let's just apply that. Let's imagine we're very clever. Well, we are clever. We can take a detailed image of the sun. The images that are produced by that Swedish telescope on La Palma have what's called a resolution of 50 meters. That is fantastic. So when you look at the sun's surface in detail, it is not evenly yellow, it's mottled like this. And this is known in the trade as granulation. In fact, my dear old professor at Oxford was one of the first people to photograph this. He went up in a balloon just after the Second World War. The balloon was in charge of a chap called Dolphus, and they took a wonderful photograph of granulation. But here we can see these granules in the sun's photosphere, and these are typically 1,000 kilometers across. They're hexagonal. They last for about 8 minutes. Now what you can see is bright stuff here, and then dark stuff. And because we're astrophysicists, the bright stuff is giving out more energy than the dark stuff, and has therefore got a higher temperature. So what we're seeing is a bubble of hot gas here, coming up, cooling, and then cold gas falling down around it. Using the Doppler principle, we can measure the velocity with which these things are coming up, and it's around about 400 meters a second. Using our astrophysics, we can measure the temperature difference between the bright bits and the dark bits, and this is about 300 Celsius, and we can take pictures progressively, and we notice that these granules last for half a minute. We can also look at the sun carefully, and we notice that it is spotty. And here we have a picture of a solar maximum sun, and we can see dark spots on the surface, sunspots. And these were first seen by a chap in England, but he didn't make much of a fuss about it. They were also seen by Galileo, who made a small fuss about it, and they were observed by Scheiner, who made a bigger fuss about it. Now, I'm not going to go into all the arguments as to who discovered sunspots, but here we have Father Christoph Scheiner doing what a typical astronomer does, and that is sit down and tell someone else to do all the hard work. And his assistant is drawing a picture of the projected image of the sun using this telescope, which has only just been invented, by the way. And this picture is being drawn day by day. And what you then notice is that if you look at the sun one day, you see a spot. Look at it the next day, the spot's moved. The day after that, the spot's moved further. And as the days progress, the spot moves across the sun. You notice straight away, from where you're sitting, that it takes this spot around about 13 days to get from the left-hand side to the right-hand side. You then say to yourself, it should then take 13 days to get around the back and come back again. Therefore, the sun is spinning every 26 days. And you've made a serious discovery. A serious discovery. You know the Earth is going around every 1 day. Here you have a chap, around about 1612, discovering that the sun is going around every 26 days. Now, if you were my student, I would then say, why? Why is the sun going around every 26 days? And here again is a question, please don't ask me. Because you haven't got the foggiest idea. When we do all the hard sums, it should be going round a lot faster, but somebody has slowed it down. And I don't know why. I mean, if I did, I'd probably have the Nobel Prize and I would own the ship and not be on it. But, this is one of the lovely things about astronomy. We come across these big problems. And then, what is even more awkward about the sun is that if we've measured carefully the spin period of the equator, goes around about every 25 days, As we move away from the equator of the sun, up to the North and the South Pole, it spins round slower and slower and slower. Ooch. This is another awkward problem, and something again which needs carefully explaining. Anyway, when we look at the sun and look at sunspots, one of the first things that scientists do is count them. One of the first scientists to do this was this gentleman, Henry Schwabe. He counted sunspots, and he noticed that the number of sunspots varied as a function of time. And so, for example, here, we're going from, well, this is the year 2000, this is 1998, this is 1996. And you can see from 1996 to 2001, the number of sunspots went up, and then from 2001 to 2008, the number of sunspots went down. And then here we are, 2008, this is 2012, the number of sunspots are going up again, and then they're going to go down again. Here's another question for you. Why is this happening? What is also interesting, that aurorae occur when you've got maximum numbers of sunspots. So in 2006, 2008, there weren't many aurorae around at all, but now it's marvellous. Get yourself to Norway and Alaska, or to Antarctica, and there'll be lots and lots of lovely aurorae for quite a few years. You notice that solar maximum lasts for quite a time. This is one of these wonderful plots that astronomers like doing, the number of sunspots as a function of time going back a bit. Here we are in the year 2000, here we in the year 1600. Remember that Copernicus was working here. You can see the numbers going up and down, up and down, up and down, and down. And then suddenly, between 1725 and 1650, the spots switched off. Why? We don't know the answer. But what happened between these 2 years was that the Earth got very cold. And this was the lovely chap, Mr. Maunder, who discovered this. And of course, this coldness made the Thames freeze. And we had fairs on the River Thames. We had what's called a little ice age. And this can quite easily happen again, sometime in the future. And will, at some unpredictable time, happen until we've worked out what's happening. So what does happen with the sun is that the energy it produces varies as a function of date. And it goes up and down. Not by a lot. If you can look here, we're only changing this by about 0.5%, but this is fairly important. These great dips here occur when big sunspots go across the sun. And the sunspots are also magnetic. Remember I told you how you could measure magnetic field by looking at Zeeman splitting. You can look at these cooler regions on the sun and measure the magnetic field in those regions. And this was done in America by these two gentlemen who completely solved the problem lesson. And here we have a father and son team. You don't get many father and son teams in astronomy, but Hal Babcock was the dad of Horace Babcock. And they produced a fascinating theory for the production of sunspots, which literally took the general magnetic fields of the sun, and then because of this differential rotation, because of the equator spinning faster than the polar regions, the sun literally wound itself up. Just like you're winding up an elastic band, and you kept winding it up until suddenly, ping, every 11 years, this sort of elasticity broke and you got a solar maximum. And this was all produced by these two chaps thinking hard and sorting out the problem. Sunspots. Marvellous regions here. A sunspot is round about 1,700 degrees Celsius colder than the photosphere. Here you can see the granulation, here you can see the spot. Why is it colder? It's simply magnetic refrigeration. Here's Earth to the same scale. So, I'm just going to finish off with some pictures of this star of ours. Here we have pictures of spotty regions with the hot gas around them. And here we can see the loops of material, magnetic plasma constriction here, having material looping up above the surface of the sun. Just look at the detail that we're getting with this picture. And this is all because we have changed. In the old days, we used to use these big telescopes on the surface of the Earth, and now, of course, we've moved up into space, and I'm just going to show you two of the space satellites that are observing the sun. This one is called TRACE. You Americans love acronyms. And this is the Transition Region and Coronal Exploration Mission. So that's what TRACE stands for. And we've got one as well. We call it SOHO. This is a joint mission between the European Space Agency and NASA. And this is the Solar and Heliospheric Observatory, which was launched in May 1996 to the L2 point, the second Lagrangian point. And this second Lagrangian point is between the Earth and the Sun, and is in fact 1% of that journey. So this second Lagrangian point is about 1,500,000 kilometers away from the surface of the Earth. And it's a very interesting gravitational balance point. A satellite that is there will stay there and will go round the Sun every year with the Earth. And so, of course, you've got a satellite here which can be energized by absorbing solar radiation, will transmit information back to planet Earth, and will be able to take pictures of the Sun at regular intervals. And so I'm just going to give you 2 or 3 typical examples of SOHO pictures. Here we can see the Sun as it is appearing in the light of ionized helium. But my favourite pictures of the Sun, which are taken by SOHO, are done in the extreme ultraviolet. And here we have a picture. The extreme ultraviolet, this is a picture taken at a wavelength of 19.5 nanometers. Well, this is not visual at all. And so you can colour it anything you like. And the artist, the astronomy artist, has coloured this one green. And here we have a, well, why it should be green, I don't know. But what is fascinating is that this is rather a crude image. We can image the Sun in more detail using the SOHO satellite. And we can at the moment take these images every 15 minutes. Every 15 minutes. We don't have to stand on Earth and wait for the Sun to come up and then say, oh dear, it's gone down, I better go home, I can't observe it until it comes up again. From SOHO, we can take an image every 15 minutes, and we've been doing that since 1996. We just think how much data we've got. Enough to keep hundreds and hundreds of science students active. Wonderful things. So, what I've been talking about, ladies and gentlemen, in this Beyond the Podium Celebrity Life series is our star, our Sun, and we're going to finish up with a picture here of what you'll be able to see, needless to say, this evening just before you go to dinner. This beautiful yellow spherical globe in the sky. I hope you've now got a bit of a feeling as to how it works. I hope you've also got a bit of a feeling of why we are so fascinated about it. And of course, the reason really is detail. When we look at the Sun using our present kit, we can see in huge detail the surface, the atmosphere. We can probe it very accurately. Whereas all the other stars in the universe are mere points, the Sun is a wonderful physical disk. And it is an object which is important. It's the highlight of astronomy. So thanks for listening, and I encourage you to go outside and have a look at it.
Poor Dr. Collins is saying he's too bright. You like his talk?
Yeah. It's interesting.